In November of 2026, a machine we launched in 1977 becomes the first object human hands have ever built to sit one full light day from Earth. Its radio voice, traveling at the speed of light, now takes about 23 hours to cross the gap back to us. Nothing we have ever made has been farther away. By the time the last of these words go quiet, the edge of the solar system will not sit where you have always placed it. The place you think of as the end will turn out to be a doorstep, with almost the whole of it still ahead, and the feeling of being sealed so far inside will settle into something steadier than it sounds right now, closer to being held than being trapped. If you find your way here on the nights when the dark outside feels a little too large, take a moment to follow along so the next one finds you when you need it. There are more of us awake out here than you would ever guess. Most people carry one of two maps of where all of this ends. On the first, the solar system stops at the last planet, somewhere past Neptune, where the worlds run out and the dark takes over. On the second, drawn by people who have read a little further, the edge is the place the Voyagers crossed more than 10 years ago, where the sun's wind finally fails and the space between the stars begins. Both maps are drawn in good faith. Both leave out almost everything that is actually out there. There is a third place, far past either one, where the true hold of the sun lets go and the rest of the galaxy comes back in, and almost no one counts it, because nothing we have launched has come close to touching it. That third place is where the solar system really ends, and it sits so far beyond the last planet that the gap between them dwarfs the whole distance from the sun to us many times over. It is late where you are, past 3 most likely, the hour when the day has let go of you and sleep has not yet taken hold. The lights are off, you are lying still, turning something over, the way people do once the noise of everyone else has finally gone quiet and the only thing left is the size of things. You did not come here for a lesson. You came because the largeness is easier to sit with when someone lays it out plainly and stays with you inside it. If any of this is landing, you already know who you are. Stay where you are. This was made for the way you are listening right now. Neptune is the last planet, and it orbits the Sun at about 30 times the distance that Earth does. Hold that number for a moment, because it is the number almost everyone stops at. 30 times as far out as we are. Out there, the sun is no longer something that warms a face or lights a sky. It is a hard white point, brighter than any other star, but still only a point. And the light leaving it takes a little more than 4 hours to reach Neptune and land on that deep blue face. 4 hours. A single beam of sunlight, crossing the whole width of the planetary system, spends most of an afternoon getting there. And this is where the map in your mind draws its line. The planets end, so the solar system ends. It is a clean story, and it is the one most of us were handed. Mercury, then Venus, then the world under your feet, then Mars, then the 4 giants, and out past the last of them, Neptune, a wall of nothing. The end. Notice what is actually holding those planets in place though, because it is the thing this whole night turns on. Not a track, not a shell, nothing you could see if you were out there watching. What keeps Neptune swinging around the sun on its slow 165-year orbit is the sun's gravity, a pull reaching out across all that dark and closing its fingers around a world 30 times farther away than we are. That pull is what I am going to call the hold. It is invisible, it is silent, and it is the only reason there is a solar system at all, rather than 8 separate worlds drifting off alone into the galaxy. Here is the first thing worth being honest about. The hold does not stop at Neptune. It cannot. Gravity does not switch off at a chosen distance the way a signal fades or a wind dies down. It weakens steadily with the square of how far you go, but it never reaches 0 on its own, only ever losing out to something stronger. So the moment you decide the solar system ends at the last planet, you have quietly assumed that the sun stops holding on just because there is nothing large enough left to see. And that is not what happens. The hold keeps going, out past the last blue world, into a dark that most people never think to look at, and it keeps finding things to grip. Think about how strange that makes the usual picture. We draw the edge at Neptune because Neptune is the last thing on the diagram The last object, big and bright and close enough to have earned a name and a place in the lineup. But the diagram is a map of the planets, and the planets were never the whole of it. They are the bright, crowded inner floor of something enormously larger. Ending the solar system at Neptune is like standing in a lit doorway at night and deciding the land stops where the light does. The dark beyond your feet still holds things. It is only unlit. And even the planets themselves are less settled than the tidy count suggests. For most of a century, the 9th planet was Pluto, out past Neptune on a tilted, stretched orbit, and children learnt its name in the same breath as all the others. Then, in 2006, the people who named these things looked at what else was turning up in Pluto's part of the sky and decided Pluto did not qualify as a full planet after all. There were too many other bodies out there of similar size, following similar paths, and Pluto was simply the first and brightest of a crowd. So the count dropped from 9 to 8, and the outer boundary of the named worlds pulled inward, though nothing at all had moved. We had only changed our minds about what we were looking at. That should tell you something about how firm this edge really is. We are not sure, even now, that Neptune is the outermost planet. For years, a handful of astronomers have watched the way certain distant icy bodies cluster their orbits, all leaning the same direction, all stretched the same way, as if something large and unseen were herding them from farther out. That something has a name already, Planet 9, and it may be a world several times heavier than Earth, orbiting so far away that it takes 10 or 20,000 years to circle the Sun once. It may also not exist at all. The clustering might be a trick of where we have happened to look. Nobody has seen it. But the fact that serious people can argue, right now, over whether there is another whole planet out there, farther than Neptune, waiting in the dark, tells you the planetary edge is only a best guess about where we have stopped finding things, and nothing like a firm wall. So keep the question in front of you. Is the last planet really the end? And feel how quickly the honest answer arrives once you look at what is doing the work. The planets are held. The whole does not stop where the planets stop. Matter does not stop where the planets stop either, as we are about to see. What ends at Neptune is only the part of the solar system that is easy to draw. Out at Neptune's distance, the hold is already far weaker than the one you know. The sun's grip on that blue world is roughly 900 times gentler than its grip on Earth, stretched thin across all those hundreds of millions of miles, 900 times weaker, and still it is enough. Still it keeps a world 4 times wider than ours, turning in a smooth, patient circle it has traced for longer than there have been oceans on Earth. That is the strange power of the thing. Even softened almost to a whisper, the hold is the loudest force out there, because there is nothing else nearby to argue with it. And that word, nearby, is the one that starts to come apart tonight. Nearby, in the space past Neptune, does not mean what it means indoors. The next planet in is more than 1 billion miles closer to the Sun. The nearest other star is so far beyond Neptune that the gap between them is not 30 times Earth's orbit, but something closer to 9,000 times the distance from here to Neptune itself. Out here, alone in all that emptiness, the Sun's faded, 1,000-fold weakened pull is still the only game there is. So it keeps reaching. It reaches past the last planet into a region we tend to imagine as blank, and it finds that region is not blank at all. Consider how the pace of things changes as you move outward, because it makes even the planetary system easy to underfeel. Earth takes a year to circle the Sun. Jupiter takes about 12. Saturn needs close to 30. Neptune, the farthest planet, takes roughly 165 years to complete a single orbit, which means that since it was found in 1846, Neptune has gone around the Sun exactly once, finishing its first observed lap in 2011. A whole human lifetime is not enough to watch the last planet make one trip. That slowing is gravity's signature. The farther out you go, the gentler the pull, and the gentler the pull, the slower a world must travel to stay in its grip, and the longer its year becomes. Hold that pattern, because it will stretch to lengths you cannot picture before this night is over, out where a single orbit swallows the whole history of life on Earth. The reason Pluto lost its place goes to the heart of what a planet even is. When the definition was written in 2006, the deciding test was whether a body had cleared its own path, whether its gravity was strong enough to have swept up or flung away the other objects sharing its lane. The 8 planets had each done this. Every one of them rules its own track. Pluto had not, and could not, because it moves through the crowded field past Neptune among countless bodies of its own kind, one member of a swarm rather than the ruler of a lane. So the demotion was really a statement about the hold. A planet, by that reckoning, is a world whose grip has won its neighbourhood. Out past Neptune, no single body has won anything at all. The whole region belongs to no one but the Sun. Feel how empty the space between the planets actually is, because the tidy diagrams mislead you here more than anywhere. If you shrank the Sun to the size of a large beach ball, Earth would be a grain of sand rolling around it some 30 paces away, and Neptune would be another grain nearly 1,000 paces out, with almost nothing in the gap but dark. The planets make no crowd, only a scatter of specks strung through an enormous emptiness, each one held on its lonely path by a grip reaching across distances that dwarf the specks themselves. When the first Voyager turned its camera back from about 40 times Earth's distance and photographed the worlds it was leaving, every planet it could catch was a single dim point of light, smaller than a dot, nearly lost in the glare of the Sun. That is the honest view of the planetary system from just past its own outer rows, a few points of light and the dark winning easily. So when we call the last planet the edge, we are confessing a bias about how we see. We notice the big bright things and assume the space between and beyond them is nothing. But the space is the main event, and the Sun's hold owns all of it, the emptiness between the planets and the far larger emptiness past them alike. One number puts the whole balance of power in place. The Sun holds more than 99.5% of all the mass in the solar system. Every planet, every moon, every asteroid and comet and grain of dust, all of it together, comes to less than half of 1% of the total, and Jupiter alone accounts for most of that scrap. So when I speak of the Sun's hold, I am not describing one body among many tugging on its neighbours. I am describing a single object that is by weight very nearly the entire system, holding a thin sprinkle of leftovers in orbit around itself. The planets are crumbs at the edge of a fire, and gravity, unlike the wind, has no wall and no fuel to run out of. It reaches from that dominant central mass in every direction, weakening with distance but never stopping of its own accord, always ready to close its grip on anything that drifts within range. That is the deepest reason the edge cannot be the last planet. The thing doing the holding does not thin out just because the bright objects do. Because past Neptune the worlds do not simply stop, they thin. The bright, close, familiar planets give way to something colder and darker and far more numerous, spread across a stretch of space so wide it dwarfs everything inside Neptune's orbit combined. We drew our line at the last planet because the last planet was the last thing we could easily point to. But the Sun's reach was never a matter of what we could point to. It goes on, quieter and quieter, and the first thing it holds beyond the planets is a field of ice we are only beginning to map. So the real question is not whether Neptune is the edge. Neptune plainly is not. The real question is what lies past the last of the planets, in the dark the hold keeps reaching into. Past Neptune the Sun's hold has loosened, but it has not let go, and the first thing it is still holding is a field of frozen bodies that stretches from about 30 times Earth's distance out to 50 times and beyond. This is the Kuiper belt, and it is the reason the space past the last planet holds far more than the emptiness you were taught to picture. A broad, flattened ring of ice and rock fills it, thousands upon thousands of worlds too small and too dark to have made the old diagrams, all of them turning slowly around the same distant white point, all of them held. Pluto lives here. That is worth sitting with, because it reframes the demotion entirely. Pluto was not thrown out of the solar system in 2006, so much as recognized as the first known citizen of this belt, a body orbiting on average about 39 times farther from the Sun than we are, one of a great population rather than a lonely ninth world. And once astronomers understood what they were looking at, the population kept growing. There is Eris, about the same size as Pluto and heavier, far enough out that a single one of its years lasts more than 5 centuries. Nearby sit Makemake and Holmeia, a stretched, spinning body shaped something like a flattened egg, turning end over end every 4 hours. Each of these is a world in its own right, cold and slow and faint, and each of them is proof that the sun's grip reaches well past the planets and keeps its hold on things we cannot see from here without a good telescope and a lot of patience. We have been out to touch one of them. On the first day of 2019, a small spacecraft that had already flown past Pluto 4 years earlier reached a body called Arakoth, about 44 times farther from the Sun than Earth. It is the most distant object our machines have ever examined up close, and what they found was not a dead grey rock, but something quietly telling. Arakoth is 2 rounded lobes joined at a narrow neck, like 2 separate worlds that drifted together so gently they simply touched and stuck, and never came apart. It is dark red, coloured by billions of years of cold chemistry, and it has sat almost undisturbed since the solar system was young. Out there, so far from the sun's warmth, nothing has happened to it. No heat to melt it, no crowd to smash it, only the long, slow turning under a grip that never quite fades. That gentleness is the character of the whole belt. The bodies here are held, but held loosely, moving at a crawl along orbits that take hundreds of years to complete. The sun is bright enough to see and far too weak to warm. Surface temperatures sit near 230 degrees below zero on the Celsius scale, cold enough that the gases you breathe would fall as frost, cold enough that water is not a liquid or a vapour, but a rock-hard mineral that behaves like stone. If you set a mountain of water ice out here, it would keep its shape for the age of the universe. The belt is a preserve of the deep freeze, holding the leftovers of the solar system's birth in a state so cold that time barely touches them. And beyond the neat outer edge of the main belt, the ice keeps going, but it scatters. There is a second, wilder population out there, the scattered disk, made of bodies flung onto steep, stretched, tilted orbits by the gravity of the giant planets long ago. These worlds swing far out and then come diving back in, following paths that lean out of the flat plane of the planets and reach distances several times greater than the belt itself. They are the belt's exiles, thrown outward but never released, still curving back because the hold, weak as it is out there, still bends their paths into loops that always return. So the honest answer to the shape of this region is that it is broad and layered and only roughly mapped. We do not know how many bodies the Kuiper belt contains, only that it is many thousands of the large ones and likely far more of the small. The true outer limit of the scattered disk is just as uncertain, because the farther out a faint icy world sits, the harder it is to catch it in the brief part of its orbit when it happens to be near enough to see. Whole categories of these objects were unknown 20 years ago. We are still finding them. The map out here is being drawn in real time, and its edges are soft. But here is the thing the belt teaches, the one plain understanding to carry forward. All of this ice, all these thousands of frozen worlds spread across tens of times Earth's distance from the sun, does not add up to a boundary. It is a population, not a wall. You can pass through it, thin as it is, and out the far side, and you will not have crossed any line that means anything. The bodies simply grow sparser and sparser until you would be hard-pressed to say where the belt ended, and the sun's pull carries on regardless, thinning with distance but never breaking. The belt does more than sit out there frozen. It feeds the inner solar system, quietly, across the ages. Most of the comets that swing through our part of space on short, regular schedules, the ones that return every few decades or few centuries, come from here, from the Kuiper belt and the scattered disk, nudged inward, one at a time, and falling toward the sun to blaze for a while before heading back out. These are the short-period comets, and they travel roughly in the flat plane of the planets, because that is the shape of the region that launched them. Keep that in mind, because much later we will meet a different kind of comet, one that falls in from every direction at once, and the difference between the two will be a clue about the true shape and size of everything the sun holds. There is a puzzle at the outer edge of the main belt that no one has fully solved. You might expect the ice to thin out gradually, growing sparser and sparser with distance, until you could not say where it ended. Instead, the population drops off sharply at around 48 to 50 times Earth's distance from the sun, far more abruptly than a slow fade would predict. Astronomers call this the Kuiper Cliff, and its cause is genuinely unsettled. Maybe the original disk of material that formed the solar system simply ran out there. Perhaps a large body, passing through long ago, swept the outer belt clean. Or there may be more ice beyond the cliff that is too dark and too distant for our surveys to catch. The honest answer is that we found a sharp edge to the belt where we expected a gentle one, and we do not yet know why it is there. The worlds themselves keep turning up, each one stranger than the last. There is Quaoar, with a ring around it that sits farther out than the rules of physics say a ring should survive. Farther out circles Gong, a slow red world on a stretched orbit that takes more than 500 years to close. Their surfaces are painted by a chemistry the deep cold allows, simple ices of methane and nitrogen, slowly darkened and reddened over the eons by the faint radiation that reaches them, coated in a ruddy tar that space chemists call tholins. These are the colours Arakoth wore, the colours of matter left alone in the freezer of the outer solar system since the beginning, changed only by time and the thinnest trickle of light. For all its breadth, the belt holds surprisingly little. Add up every icy body out there, and the whole Kuiper belt likely comes to no more than a few % of the mass of Earth, spread across a ring tens of times wider than the orbit of Neptune. It is broad, and it is nearly empty, a thin scattering rather than a dense field, which is part of why crossing it means nothing in particular. A spacecraft can pass straight through and meet nothing at all, but what little is out there is precious in a way the inner planets are not. These frozen bodies have sat in the deep cold since the solar system was assembling, too far out and too undisturbed for heat or collisions to have reworked them. They are samples of the original material, the actual leftover stuff the planets were built from, kept in cold storage for 4.5 billion years. When a spacecraft flew past Arakoth and found two lobes gently joined, it was looking at a moment from the birth of the solar system frozen in place, a record of how the first small bodies came together without being smashed apart. The belt is thin and cold and quiet, and it is also the best preserved archive we have of where everything came from. The one machine that has reached it is still out there now, still working, still creeping toward the belt's outer thinning, listening for whatever lies past the ice. Which means the belt cannot be the edge you came looking for. Ice does not make an edge, it makes a region, and if you are hunting for a real boundary, a place where something actually changes, a place where you could point and say, the character of space is different on this side than on that side, you will not find it in the Kuiper belt. You will have to look for a boundary made of something other than frozen bodies. There is such a boundary, it sits farther out than the main belt, and it is made of the sun itself, rather than of ice or rock, of the thin, ceaseless breath the sun exhales in every direction, a wind of charged particles streaming outward at hundreds of miles every second. That wind fills the space around all the planets and all the ice, a bubble blown by the star at the center, and it reaches out until, at some distance, it can push no farther. Where that wind finally slows is the first true boundary the sun makes, sharper and stranger than anything the belt could offer. So leave the ice turning behind you, still held, still slow, and follow the wind outward, because the next question is a simple one with a surprising answer. Where does the sun's own breath finally run out of the strength to blow? The sun holds the planets two ways at once, and until now, I've only shown you one of them. There is the pull, the gravity that keeps the worlds turning, and there is a push, a steady outward breath the sun exhales that fills the whole space around it. That breath is the solar wind, a thin stream of charged particles boiling off the sun's outer layers and racing outward in every direction at speeds of hundreds of miles a second. It never stops. Every second of every day, the sun sheds about 1 million tons of itself into space this way, and that outflowing gas inflates a bubble around the entire planetary system, a region where the sun's own material, not the material of the wider galaxy, is the thing you would be moving through. For most of the distance out from the sun, that wind blows faster than sound. Not sound in air, which cannot exist out there, but sound in the thin plasma itself, the speed at which a disturbance can ripple through that gas. The wind screams outward faster than its own ripples can travel back, and as long as that is true, the wind is in charge, sweeping the space ahead of it clean, pushing the interstellar material back. But the wind is also thinning as it goes, spreading out over a larger and larger sphere, losing pressure with every mile, and somewhere far past the planets it finally runs into something it cannot simply shove aside. It runs into the pressure of the galaxy itself, the diffuse gas and the faint magnetic field of the space between the stars, pressing inward from all sides. Where those two pressures meet, the wind does something abrupt. It slows down, all at once, from supersonic to subsonic, dropping below the speed of its own ripples in a sudden shock. This is the termination shock, and it is the first genuine boundary the sun makes. The first place where you could say the character of space changes sharply, rather than fading by degrees. Ahead of it the wind is fast and thin and cold. Behind it the wind is slow and dense and hot, piling up, heating as it compresses, its magnetic field bunching and strengthening as the flow stacks against the pressure from outside. We know exactly where this happens because we have crossed it. Both Voyager spacecraft, launched in the same year and sent on slightly different paths out of the solar system, punched through the termination shock and lived to report it. The first crossed in December of 2004 at about 94 times Earth's distance from the Sun. The second crossed in August of 2007 at about 84 times that distance, 10 units closer in than its twin. The difference in those numbers is itself part of the story, because it tells you the boundary is not a perfect sphere. The bubble is squashed and lopsided, pushed in on one side by the direction the whole solar system is travelling through the galaxy, the way a bubble around anything moving through a fluid gets pressed at the front. And the boundary is not even fixed in place, it breathes. The sun runs on an 11-year cycle, growing stormy, and then calm, and then stormy again, and as its output rises and falls, the pressure of the wind rises and falls with it. When the sun is active and blowing hard, the termination shock is pushed outward. As the sun quiets, the shock drifts back inward. Over the years it can move by several times Earth's distance from the sun, in and out, like the wall of the bubble flexing with the breathing of the star at its centre. When the second Voyager crossed the shock, it actually crossed it more than once, catching the boundary in the act of sliding back and forth across the spacecraft as the pressure shifted. So picture what is happening at that boundary, in plain physical terms. A thin gas, so sparse that by any earthly measure it would count as a hard vacuum, is racing outward faster than sound. It reaches a distance where it can push no farther, and there it slams, in the space of a short stretch, from that supersonic race down to a slow, churning crawl. Heating as it stops, its temperature climbing into the hundreds of thousands or even millions of degrees as all that motion turns into heat. The gas is so thin that this searing temperature would not burn you the way a flame would, because there is almost nothing there to carry the heat. But the particles themselves are moving with tremendous energy, and the field that threads them grows stronger, and the smooth outward wind becomes a hot, turbulent, piled-up mess. That is the termination shock, and that is what the edge of the sun's breath looks like. Now here is the question that matters, the one that decides whether this is the edge you have been looking for. Is the termination shock the edge of the sun? And the honest answer is that it is the edge of the sun's wind speed, and nothing more. It is the place where the outward breath stops racing and starts crawling, a real boundary, a sharp one, a thing you can cross and measure. But it is not the end of the sun's influence, not by a long way. The wind is still there past the shock, slowed but present, and the sun's gravity, the pull, is entirely untouched by any of this. The push has begun to fail, the pull has not even noticed. It helps to know where that wind is born, because the birthplace is as strange as the boundary. The sun's visible surface sits at about 6,000 degrees, hot enough to blind you, but just above it lies the corona, the sun's thin outer atmosphere, and the corona runs hotter than the surface beneath it, not cooler as you might expect, wildly hotter, reaching 1,000,000 degrees or more. Why the corona is so much hotter than the surface beneath it is one of the oldest unsolved problems in the study of the sun, still argued over today. But hot it is, and matter that hot cannot be held down. It boils off the top of the corona and streams away into space. And that streaming gas is the solar wind, the outward breath we have been following. The bubble it inflates has a name, the heliosphere, and it is the largest single structure the sun actively makes, a chamber of the sun's own material carved out of the galaxy. The wind does not blow in a simple straight line either. The sun spins once about every 27 days, and as it spins it drags the roots of its magnetic field around with it, so the field threaded through the outflowing wind winds up into an enormous spiral, like the curved arc of water thrown from a spinning sprinkler. By the time this spiral reaches the outer solar system, it has wrapped around many times, and the Voyagers, crossing the termination shock, passed through a magnetic field far more tangled and layered than the neat lines a still sun would produce. The shock itself turns out to be a place where particles are flung to high energies, a natural accelerator out at the rim of the bubble, and some of the cosmic rays the spacecraft detected there were born not in distant exploded stars, but right at that boundary, whipped up by the shock as the wind slammed to its halt. And the whole bubble is lopsided, because the sun is not sitting still. The entire solar system is ploughing through the gas of the galaxy at tens of thousands of miles an hour, and that motion presses the bubble in at the front and draws it out at the back, the way anything moving through a fluid gets squeezed ahead and stretched behind. So the termination shock is closer to the sun in the direction we are heading, and farther in the direction we have been, and the difference in where the two Voyagers crossed it, 10 units apart, is partly a map of that lopsided shape, the bubble bluntest on its leading face. The wind is not even a single steady breath. It comes in two kinds, a fast wind pouring from the open regions near the sun's poles at something like 1.5 million miles an hour, and a slower, denser wind seeping from nearer the equator at about half that pace. The two streams chase and collide as the sun turns, building ripples and shocks that roll outward through the whole bubble. And wherever the wind goes, it carries the sun's magnetic field locked into it, dragged along like dye in a current, so that the field we measure at the far edge of the solar system is the sun's own field, stretched and wound and carried outward on the back of the wind across billions of miles. This matters for more than physics out at the rim. The bubble the wind inflates is also a shield. It holds back a large share of the galactic cosmic rays, the high-energy particles racing in from exploded stars across the galaxy, deflecting them before they can reach the inner planets. Life on the world under your feet has spent its whole existence sheltered inside the sun's breath, partly screened from that constant rain of radiation by the very bubble whose outer wall the Voyagers just crossed. The wind is a boundary, and it is also a kind of protection, and both of those things end at the same place. You can see the wind's fingerprint without leaving the inner solar system if you know where to look. When a comet swings near the sun and grows its glowing tail, that tail does not stream out behind the comet the way smoke trails a moving train. It points away from the sun, always, whichever way the comet happens to be travelling, and as the comet rounds the sun and heads back out, the tail swings around to keep facing away from the light. That is the solar wind at work, blowing the comet's loosed gas and dust outward, and it was one of the first clues, long before any spacecraft existed, that the sun pours a steady stream of particles into space in every direction. The wind writes its presence across the sky in the tails of comets, and that same stream, reaching all the way out to the shock and the sheath and the wall, is the thing that carves the whole bubble we have spent this time crossing. That is the split that will run through the rest of this. Out here, the two forms of the hold come apart. The push, the wind, is a finite thing with a definite outer wall, and we are approaching that wall now. The pull, the gravity, is a different animal entirely, thinning without end, reaching so much farther that the wind's whole bubble will turn out to be a small bright chamber near the very center of the sun's true domain. But we are not there yet. Right now we have only crossed the first wall, the place where the breath slows, and beyond it lies a strange, hot, churning shell, a region no one expected to be shaped the way we found it. So the next question is, what waits in that shell, in the space past the shock and before the true end of the wind? What is it like inside the slowed breath of the sun? Past the shock, the hold is thinning fast, the wind's push nearly spent, and what it leaves behind is a shell of hot, slow, churning gas that behaves like nothing else in the solar system. This is the heliosheath, the region between the place where the wind slows and the place where it finally stops. It is the outermost layer of the sun's bubble, the last of the sun's own breath, before the space of the galaxy takes over, and for a long time we could only guess at what it was like. Now 2 spacecraft have spent years crossing it, and some of what they found does not match anything we predicted. Inside the heliosheath, the wind is no longer racing. It has slowed at the shock, and now it drifts, warm and dense and confused, its once smooth outward flow broken into eddies and swirls. The particles here are strange ones. Many of them are what physicists call pickup ions, atoms that drifted in from interstellar space as neutral gas, made it deep into the bubble untouched, and then were stripped of an electron and caught up by the sun's magnetic field, suddenly energized to enormous speeds. These pickup ions carry much of the pressure out here, and they make the heliosheath hotter than the models expected, a shell of thin plasma at temperatures reaching into the millions of degrees, though so sparse that the heat is a matter of energy per particle, rather than anything that could warm a surface. The magnetic field the Voyagers found here was not the smooth spiral they carried outward from the inner solar system either. It had bunched up, layered itself into sheets, folded and stacked as the slowed wind piled against the pressure from outside. Moving through the heliosheath, the spacecraft passed through zones where the field went quiet and zones where it thrashed, regions of calm and regions of turbulence, a boundary layer far messier and more structured than a simple bubble wall has any right to be. But the real surprise was the size. Before the Voyagers reached it, the best models of the sun's bubble predicted that this outer shell should be thick, that the distance from the termination shock to the true outer wall should be something like 50 to 70 times Earth's distance from the sun. The spacecraft crossed it in far less. In the direction the Voyagers travelled, the heliosheath turned out to be only about 30 units thick, less than half of what the models called for. The wind's bubble had a thinner skin than anyone had drawn, and more than a decade later, that thinness still has no agreed explanation. Something is compressing this shell, or draining energy out of it, or shaping it in a way the models miss, and the people who study it are still arguing over what. The honest position right now is that we crossed the outer layer of our own star's bubble and found it built differently than our best physics said it would be. That admission is worth pausing on, because it cuts against the confidence the rest of this can seem to carry. We are talking about the structure of our own solar system, the immediate surroundings of the only star we have ever lived beside, and we still cannot fully explain the shape of its outermost shell. 2 spacecraft had to physically fly into it before we learnt that our models were off by more than half. This is the nearest example there is of the boundary between a star and the galaxy, and it surprised us. Whatever certainty you hear in the numbers farther out, hold it a little more loosely after this. The heliosheath is a reminder that the edge of a star is a subtle thing, and that reasoning from the inside about what the outside looks like has a way of going wrong. We did not have to wait for the Voyagers to reach the shell to start mapping it either. A small spacecraft in orbit near Earth, built to study exactly this boundary, spends its time catching a rare kind of messenger, atoms that fly all the way in from the edge of the bubble after being knocked loose out there. From those incoming atoms it builds a picture of the whole far boundary at once, a map of the rim drawn from the centre. And when it first delivered that map, it showed something no one had predicted. Arcing across the sky was a bright, narrow ribbon, a band where far more of these atoms were coming from than anywhere else, as though the edge of the bubble glowed brighter along one great curved line. Nothing in the models called for a ribbon. Years later, there is broad agreement that it is shaped by the magnetic field of interstellar space draping over the outside of the bubble, pressing in along a particular line. But the details are still worked out and revised. Our own star's outer boundary surprised us again, this time with a feature we are still explaining. The Voyagers found their own surprises inside the shell. In one stretch, the first spacecraft passed through what the scientists described as a sea of magnetic bubbles, a frothy, foamy zone where the piled-up magnetic field had broken into separate pockets, each one wider than Earth's distance to the Sun, a churned magnetic foam at the rim of the Sun's domain that no simple picture of a smooth bubble wall had prepared anyone for. And the bubble almost certainly does not end in a neat round shape. Downwind, in the direction opposite the Sun's motion through the galaxy, the heliosphere probably trails off into a long tail, the way a comet trails its own material behind it, stretched out by the same motion that blunts the front. Some measurements suggest the tail is split into two lobes rather than one smooth streamer. We cannot see the far end of it, and we may never send anything down that direction to find out. So the true three-dimensional shape of the Sun's wind bubble, the exact form of the space our star has cleared for itself, remains partly a matter of inference and argument, a thing we are still learning the outline of from the inside. Hold in mind how thin all of this really is. The plasma of the heliosheath, hot as it runs in temperature, is so sparse that only a few of its particles might be scattered through a space the size of a beach ball, a gas emptier than the best vacuum any laboratory on Earth can make. The heat is real in the sense that each particle moves with tremendous energy, but there are so few particles that nothing solid passing through would feel any warmth at all. This is the strange truth of the outer boundary. It is searing and freezing at once, a near-perfect emptiness that also registers as millions of degrees, and it takes instruments built for exactly this to make sense of a place so far outside ordinary experience. The Voyagers did not flash across the shell either. Each spacecraft spent years inside it, crossing slowly, sending back reading after reading as the seasons passed on the world they had left, drawing a thin thread of measurement through a shell tens of times Earth's distance deep. And here is the humbling part. Everything we know about the structure of the Sun's outer boundary, its thickness, its foam of magnetic bubbles, its churning field, we know from exactly two crossings, two narrow lines of data punched through one enormous three-dimensional shell at two nearby points, in nearly the same direction. We have never sampled the sides. The tail is just as unknown to us. The entire detailed picture of our own star's edge rests on two threads through a sphere, and everything between and beyond those threads is a reasoned guess. When you hear a confident description of the shape of the heliosphere, remember that it is drawn from two faint dotted lines and a great deal of careful inference. Still, for all its strangeness, the heliosheath answers one question cleanly. Have we left the solar system yet, out here in this churning shell? No, not in any sense that matters. This is still the Sun's own material around you, the Sun's own wind, slowed and heated and knotted up, but still the Sun's, still pushed outward by the star at the center, rather than pressing in from the galaxy. You are inside the breath, near the far reach of it, in the last layer before it gives out, but you have not crossed into the space between the stars. The wind still surrounds you, and as long as the wind surrounds you, you are within the Sun's bubble, within the part of space the Sun's push has cleared and claimed. The wind will end though. Somewhere past this hot, confused shell, there is a final wall, a place where the Sun's outflowing gas meets the interstellar gas head-on and can push no farther at all, where the last of the breath stops and the galaxy's own material begins. That wall is the true outer skin of the bubble, the place most people have in mind when they say a spacecraft left the solar system. It is sharper than the shock and stranger, and we have crossed it too, and the crossing was recorded not as a wall struck, but as a number changing, quietly, in the dark. So the question narrows to its finest point. Where exactly does the Sun's wind end for good, and what happens when you pass out of your own star's breath into the space between the stars for the first time? The wind's hold ends at a single sharp wall called the heliopause, about 121 times Earth's distance from the Sun, and past it the Sun's gravitational hold carries on unseen, as if nothing had happened. This is the boundary that gets the headlines. When you read that a spacecraft has left the solar system and entered interstellar space, this is the line being crossed, the true outer skin of the Sun's bubble, the place where the Sun's own wind finally meets the wind of the galaxy, and neither can push past the other. On the inside, hot, thin plasma streaming out from our star. On the outside, cooler, denser plasma drifting between the stars. The heliopause is the surface where those two touch. The first Voyager crossed it on the 25th of August, 2012, at about 121 times Earth's distance out. The second crossed 6 years later, in November of 2018, at about 119 times that distance, the two numbers close enough to tell us the wall sits at a fairly consistent depth in the directions the spacecraft travelled. And the way we knew the crossing had happened is one of the quietest, strangest things in the whole story. The first Voyager could not measure the wind directly at that point. The instrument built to taste the solar wind, to feel its speed and direction, had failed back in 1980, more than 3 decades before it reached the wall. So there was no dramatic reading of the wind dropping to nothing. Instead, the confirmation came from a different set of counters, the ones that track cosmic rays, the high-energy particles that come flying in from the wider galaxy, from distant exploded stars and violent events far away. Inside the Sun's bubble, those galactic particles are partly held back, deflected by the Sun's wind and magnetic field, so their count stays low. As the spacecraft approached the heliopause, that count began to climb. And then, over a matter of days in that late August, it jumped and stayed high, while the particles native to the Sun's own bubble fell away almost to nothing. A number went up, another number went down. In the dark, more than 11 billion miles from home, a machine crossed out of its own star's breath and into the galaxy, and the only announcement was a set of counts changing on an instrument that was never designed to be the one that told us. That is how the most talked about edge in the solar system actually reveals itself. Not as a barrier, not as a flash, but as a shift in the kind of particles around you. You would feel nothing crossing it and see nothing. The plasma on the far side is denser than the plasma on the near side, but both are so thin they count as vacuum. The only way to know you had passed was to watch the character of the tiny things streaming through and notice that they had changed allegiance, that you were now being peppered mostly by the galaxy, rather than shielded mostly by the Sun. And even this crossing, clean as it looks in hindsight, was not something everyone agreed on at first. When the first Voyager's counts jumped, some careful scientists argued that the spacecraft might still be inside the bubble, that the magnetic field had not changed direction the way a true crossing should, that we might be seeing some strange fold in the boundary rather than a clean exit. The debate ran for months. It took more data, and eventually the second spacecraft's crossing years later, to settle most of the doubt. Even now, a small number of researchers will tell you the picture is more complicated than the headlines allow. This is the nearest edge of its kind, the one boundary of this sort we have physically crossed, and we still argue about the details of what crossing it means. But here is where the whole night turns, so hold it carefully. Suppose we grant the crossing entirely. Suppose the Voyagers truly passed the heliopause and now fly through interstellar plasma, the material of the galaxy, rather than the material of the Sun. Does that mean they have left the solar system? They have left the Sun's wind. That much is real and measured. They are outside the bubble the Sun's breath inflates, beyond the reach of the outward push. But the wind was only ever one of the two forms of the hold, and it was always the weaker, more finite one. The other form, the gravity, the pull, does not end at the heliopause. It does not even weaken noticeably there. The heliopause is set by a balance of pressures between two thin gases, and gravity has nothing to do with where that balance falls. So the Voyagers crossed out of the Sun's breath while remaining utterly, completely inside the Sun's gravitational grip, held as firmly as they were the day before, curving ever so slightly under a pull that will keep bending their paths for tens of thousands of years to come. The second Voyager gave us the crossing the first one could not. Its own wind detector, unlike its twins, was still alive when it reached the wall in 2018, so it caught the moment directly. As it passed out of the sun's bubble, the plasma around it changed character in exactly the way the theory predicted, but no one had ever measured. The thin hot gas of the sun's own wind gave way to a colder, denser gas, and the density around the spacecraft jumped sharply upward as it crossed into the galaxy's material. For the first time, we had a direct reading of both sides of the wall, the sun's plasma on the inside and the interstellar plasma on the outside, taken by an instrument built for the job. The two accounts, the first Voyager's rising cosmic ray count and the second Voyager's rising plasma density, told the same story from two different angles, and together they made the crossing about as certain as a thing measured once, in the dark, 11 billion miles away, can ever be. Then came the strangest gift of all. A few years after it crossed, the first Voyager began sending back a faint, steady tone from the plasma around it, a persistent hum from the interstellar gas itself. The instrument that catches plasma waves had picked up a thin, monotone drone, so quiet it took careful listening in the data to find the sound of the galaxy's own gas rippling around the spacecraft. The researchers who found it compared it to a gentle, endless rain, with the sun's occasional outbursts arriving like distant thunder before the rain returns. What that hum lets us do is worth pausing on. It reports the density of the space the spacecraft is swimming through continuously, whether or not the sun is doing anything, so that for the first time we can feel our way through interstellar gas in real time, mile after mile, from a machine already beyond the wall. None of this changes the deeper fact though. The wall the Voyagers crossed, sharp as it is, measured now from two sides and singing its faint plasma song, is set entirely by the meeting of two thin gases. It is a pressure boundary, a place where the sun's breath and the galaxy's breath come to a standstill against each other. Gravity plays no part in fixing where it lies. There was one reading that did not behave. When a spacecraft crosses out of the sun's bubble, the magnetic field around it should swing to a new direction, from the sun's field to the galaxies. And that swing was one of the signs scientists waited for to confirm the crossing. But the field barely turned. On both Voyagers, the direction of the magnetic field on the far side of the wall looked oddly similar to the direction on the near side, as though the sun's field and the galaxy's field happened to line up, or as though the boundary were doing something to the field that no one had expected. It remains one of the open puzzles of the crossing, a small stubborn detail that did not fit the tidy story, and a reminder that even the boundary we have physically passed still holds surprises we cannot fully explain. Notice too that the two spacecraft did not agree on where the wall sat. One crossed at about 121 times Earth's distance, the other at about 119, 6 years apart, in different directions. Even that small difference tells you the boundary is no fixed sphere, but a living surface that flexes with the sun's moods and the pressures of the galaxy, breathing in and out over the years the way the shock before it does. This is the trick the word interstellar plays on us. The Voyagers are in interstellar space in the sense that they float in the galaxy's plasma now, rather than the sun's. They are nowhere near interstellar space in the sense of having escaped the sun's hold, because that hold reaches 1,000 times farther than the wall they crossed. Calling the heliopause the edge of the solar system is like calling the edge of a lantern's glow the edge of the field it stands in. The light stops, the ground does not. The sun's wind stops at the heliopause. The sun's ownership of the space around it goes on and on. So the wind gives us a clean, measurable, honest boundary, and that boundary marks the edge of one of the two things the sun does, rather than the edge of the solar system itself, which forces the real question, the one that will carry us the rest of the way out. If the gravity reaches so much farther than the wind, if the pull does not end where the push does, then how far does it actually go? How far past the heliopause does the sun keep holding on, and what is out there in the enormous dark between the wall of the wind and the true end of the grip? The hold is still taut across an almost unbelievable distance, because the two machines that cross the wind's wall are still out there, still falling outward, still gripped. The first Voyager is now about 170 times Earth's distance from the sun, and climbing by roughly 3.5 of those units every year. The second is a good deal closer in, at about 143 times Earth's distance, having taken a slower path. These are the farthest things we have ever made. Everything else humanity has ever built or launched is somewhere behind them, closer to the sun, and every year the gap widens. Let me be careful about a claim you often hear, because it is usually stated wrong. The first Voyager is not the fastest object we have ever built. That title belongs to a different spacecraft entirely, the Parker Solar Probe, which dives in close to the sun and then gets whipped to speeds of around 430,000 miles an hour, far faster than any Voyager. What the first Voyager holds is a narrower and stranger record. It is moving away from the sun faster than anything else we have ever set loose, carrying the highest outward speed, the highest escape speed of any object we have sent into the dark. Moving at about 17 kilometers every second, a little over 60,000 miles an hour, it is the fastest thing we have ever aimed outward and let go, straight away from home and never coming back. And in November of 2026, it reaches a mark nothing we have made has ever touched. It becomes the first human object to sit one full light day from Earth. That means the distance light itself covers in a single day, moving at the fastest speed the universe allows. A beam of light which crosses from the Sun to Earth in about 8 minutes, and from the Sun to Neptune in about 4 hours, needs a whole day to reach the first Voyager. Turn that around and you feel the loneliness of it. When we send the spacecraft to command, the instruction crawls outward at light speed for close to 23 hours before it arrives. When the spacecraft answers, its reply takes close to 23 hours to come back. A single round of conversation with our own machine now takes the better part of 2 days, and every year that pause grows longer. Picture the two of them out there, in plain terms. Small, cold, decades old, built with computers weaker than the one you fell asleep holding. Around them, no wind of the sun anymore, only the thin plasma of the galaxy. Behind them, the sun reduced to a single brilliant point, the brightest star in a black sky, but only a star now, giving no warmth, casting no light you could read by. They orbit nothing, and they are not slowing in any way you would notice, only falling outward along paths bent so gently by the sun's distant grip that over a human lifetime the curve is almost too slight to see. The hold is faint out here, hundreds of times weaker than what keeps Earth in place, and still it has them. Still every mile they travel is a mile the sun permits, on a leash so long it seems like freedom. They are also dying, slowly, and we should be honest about that too. Each spacecraft is powered by the steady heat of decaying plutonium, and that heat fades a little every year, by about 4 watts of electrical power annually, until there is not enough left to run the instruments. One by one, over the years, the science instruments have been switched off to save power. The heaters have been shut down. Parts of the spacecraft that have not been warm in decades sit at temperatures their designers never tested. Within a few more years, both machines will fall silent for good, not destroyed, not stopped, simply too starved of power to whisper back across that widening gap. And then they will keep going anyway, dark and quiet, still falling outward, still held, carrying their engraved golden records and their silence into the space between the stars for as long as the galaxy lasts. Each of the 2 spacecraft carries something that will outlast every working part of it, a golden record fixed to its side, a plated disc holding sounds and images of the world that made it, greetings in dozens of languages, music, the noise of rain and heartbeats and wails. It was placed there on the small chance that some far future finder, ages from now, might play it and learn that we existed. The spacecraft will be dark and silent within a decade. The record will keep its grooves for hundreds of millions of years, drifting through the galaxy long after the sun has forgotten the machines that carried it. A message with almost no chance of ever being read and no way to be recalled. The Voyagers are not aimed at anything. They fall outward along fixed paths, and the stars, which also move, happen to drift across those paths from time to time. In about 40,000 years, the first Voyager will pass within roughly 1.5 light years of a dim red star called Gliese 445, closer to that star than to our own sun, though still far too distant to be caught by it. The second Voyager will slide within a similar reach of another faint star, Ross 248, in about the same span of time. These are not destinations so much as near misses across the dark, chance approaches to strangers, and after each one the spacecraft will drift on, still unclaimed, still coasting, on and on for as long as the galaxy turns. And the two of them are not alone in leaving. 5 machines in all are now falling out of the solar system on paths that will never bring them back. The 2 Voyagers, the 2 older pioneers that went silent decades ago, and the newer craft that flew past Pluto and Arakoth. Together they are the entire outbound fleet of our species, everything we have ever launched hard enough to escape the sun's return, and every one of them is either already dead or dying, coasting outward under the same faint grip, carrying our machines and our silence into the same enormous dark. That is the whole of it. 5 small objects, 5 decades of trying, all of them still deep inside. Consider what it takes to still be hearing from them at all. These are machines built in the early 1970s, running on computers with less memory than a musical greeting card, powered by the slow warmth of decaying plutonium that fades a little every year. To keep them alive, engineers have spent decades switching off one system after another, shutting down heaters, powering down instruments, coaxing the last useful work from a dwindling trickle of electricity. Parts of each spacecraft now sit far colder than anything they were ever tested for, and still they answer. By the time a signal from the first Voyager reaches Earth, after close to a full day crossing the dark, it has spread so thin that the power arriving is almost beyond belief, a whisper so faint that only antennas tens of yards across, aimed with great care and listening hard, can catch it against the noise of the sky. We are straining to hear a machine calling out with less power than the bulb inside a refrigerator, from a distance where its voice takes most of a day to arrive. And within a few years even that will end. The power will fall below the level needed to run a single instrument, the last transmitter will fall silent, and the 2 of them will keep coasting outward without a word, no longer reporting, simply falling, held by the same grip that has never once loosened. Everything humanity ever learns from out past the wind will have come from these 2 failing voices, and then the voices will stop, and the machines will go on. There is something worth saying about where they are pointed and how long they will last. The first Voyager is climbing out of the flat plane of the planets, heading up and away toward the northern reaches of the sky. The second is diving the other way, down and south. Neither is aimed at a target, and after their chance passes by distant stars tens of thousands of years from now, they will simply keep going, settling into orbit around the center of the galaxy itself, circling the Milky Way among its hundreds of billions of stars for as long as the galaxy holds together. They will almost certainly outlast the sun. Billions of years from now, when the sun has swollen and cooled and died and the Earth is long gone with it, these 2 small dead machines and their golden records will still be out there, coasting through the galaxy, carrying nearly the only lasting trace that we were ever here. That is the strange dignity of the outbound fleet. The machines fall silent within a decade. The falling, in the deepest sense, never ends. So set the question plainly. These are our farthest reaches, nearly 50 years of coasting, 17 kilometers every second, 1 full light day from home, the most distant things our species has ever placed in the universe. Surely, after all that, they must be nearly at the edge. Surely the true boundary of the sun's hold cannot be much farther, when we have already come so unthinkably far. Feel how much that assumption wants to be true. We have crossed the shock, we have crossed the heliosheath, we have crossed the heliopause and entered the galaxy's own plasma. A light day out, we are still climbing. Every instinct says we are close, that the finish line of the solar system must be somewhere just ahead, that a species which has reached this far has surely reached most of the way. Hold that feeling, because it is about to break. The gravity reaches so much farther than the wind that everything we have just crossed, the shock and the sheath and the heliopause and all the miles beyond, turns out to be a small bright chamber near the very center of the sun's true domain. The 2 Voyagers, our farthest and fastest outbound machines, are light day record holders, have not crossed 1% of the way to the real edge. They have not crossed 1/10 of 1%. So the question that opens the middle of this becomes almost cruel in its simplicity. If a light day out is nothing, if 50 years and 17 kilometers a second is barely a start, then how far is the real edge measured honestly against the farthest we have ever reached? Here is the number that should tip the floor out from under you. The first Voyager, after nearly 50 years of falling outward, moving away faster than anything we have ever released, sitting one full light day from home, will need about another 300 years just to reach the inner edge of the region we are heading toward. And it will need something closer to 30,000 years to pass all the way through it and out the far side. 300 years to reach the beginning of the true outer boundary, 30,000 years to leave it behind. Sit with those spans against the life of the machine making them. The Voyagers will be silent within a decade, dead, dark, coasting. 300 years from now, when the spacecraft finally reaches the near edge of the outer solar system, there will be no signal, no instrument, no one listening, only the cold body of the thing drifting across a line it can no longer report. And that is merely the beginning of the boundary. To cross it, to pass from its inner edge to its outer one, the dead spacecraft will spend 300 centuries. 30,000 years is longer than all of recorded history many times over. It is longer than our species has looked the way it looks now. And it is the time our fastest outbound machine needs to traverse just the final shell of the sun's domain, a shell it will not even reach for another 3 centuries. Put it as a fraction, and it gets worse, not better. The far edge of the sun's hold sits at something like 100,000 times Earth's distance from the sun, and may reach considerably farther. The first Voyager is at 170 times that distance. Divide one into the other. Our farthest reach, the most distant object in the history of the human species, has travelled less than 2/1000ths of the way to the edge of its own solar system, roughly 1 part in 600. If the full distance to the true edge were the length of a football field, everything we have ever launched, in 50 years of trying, would sit within the first 6 inches of the goal line. This is the vertigo. Not that space is large, which you already knew, but that we are sealed so deeply inside our own small corner of it, that our greatest feat of reaching barely clears the doorway. We tell the story of the Voyagers as a story of leaving, of escape, of humanity finally stepping out of the solar system and into the galaxy. And the truth is that they have stepped from the innermost chamber into the next chamber. And there are chambers upon chambers still ahead, and the outermost wall is 1,000 times farther than the wall we made so much of crossing. We are not leaving, we have not left. On the scale of the thing that actually holds us, we have not meaningfully moved. And the strangest part is that the hold is still there, the whole way out. That is what makes this enclosure, rather than mere distance. If the sun let go somewhere out past the Voyagers, if there were a clean line beyond which we were simply free, adrift in a galaxy that owed us nothing, that would be one kind of feeling, a lonely one. This is a different feeling. The sun does not let go. Across that entire unthinkable gap, from the Voyagers at 170 units, all the way out to 100,000 and beyond, the grip is still closed, weaker than weak, stretched to almost nothing, a pull so faint that at those distances it can barely be measured, and still a pull, still a hold. Everything in that gap, and there is a great deal in that gap, is falling around the sun on orbits the sun still governs. We are not near the edge, and everything between us and the edge is still, quietly, ours. Measure the gap against light itself, and the enclosure gets harder to shrug off. Light crosses from the sun to Earth in about 8 minutes. It reaches the far edge of the sun's hold, more than a light year out, only after more than a year of travel, at the fastest speed the universe permits. So even a beam of light, the quickest messenger there is, would need over a year just to cross from here to the true boundary. Our fastest outbound machine moves at about 1/10,000th of that speed. Set beside light, the Voyagers are not crawling so much as very nearly standing still, and the edge they are aimed at lies more than a light year away, through a medium that makes even light take its time. No craft we have built or seriously planned changes this. The spacecraft that flew past Pluto left Earth faster than any before it, and it too would need tens of thousands of years to reach the outer shell. There is no engine on any drawing board, no plan on any desk that brings the true edge within a human span, or within 100 human spans, or within the whole length of recorded history stretched end to end. To send something to the inner edge of the outer solar system and have it arrive intact would mean building a machine that keeps working for 3 centuries, roughly 10 human generations handing the watch to one another with nothing to show for it in their own lifetimes. To reach the far edge would take 1,000 generations or more. We are not talking about a hard trip. We are talking about a distance that outruns the idea of a trip altogether. This is the honest weight behind the way we tell the story. We say the Voyagers left the solar system, and we mean it as an ending, a graduation, humanity stepping out into the galaxy at last. Held against the real edge, it is closer to a first breath than a departure. We have not left. On the scale of the thing that actually holds us, we have taken the smallest possible step away from the center and stopped, and everything we call interstellar exploration has happened within the first fraction of a percent of the way to our own front gate. Try to hold the 30,000-year figure against something human, because the number alone slides off the mind. 30,000 years ago, the people who would become us were painting animals on cave walls by firelight, living through the depth of the last ice age, tens of thousands of years before the first field, the first city, the first written word. All of recorded history, every empire and language and invention you have ever heard of, fits many times over inside that span. And that is merely the time our fastest dead machine would need to cross the final shell of the sun's domain. A shell it will not even reach for 3 more centuries. Stretch a single human life across that distance and it disappears entirely. Stretch the whole of civilization across it and it barely reaches. The edge is far in the way the deep past is far, and not in the way another country is far. A distance measured in the rise and fall of whole species, and our reaching, for all its wonder, has covered a sliver of it that rounds down to nothing. You can hear that as a wall closing in, and right now, in the middle of this, that is probably how it lands, so far inside, so far from any edge, sealed by a grip you did not choose and cannot break, in a domain so wide that the fastest thing your species ever built will spend 30,000 years crossing only its final layer. The dark you have been turning over all night just got larger by a factor you have no way to feel, and the part of it that belongs to the sun, the part you are trapped inside, is almost all of it. But before that thought can harden into pure dread, notice the thing that saves it, the thing the fraction hides. That enormous gap between our farthest reach and the true edge is not empty. We speak of the space past the Voyagers as if it were 300 years of nothing, followed by 30,000 years of nothing, a blank waiting to be crossed. It is not blank. The sun did not spend its faint outer grip on empty dark. It filled that space, or rather it kept what was always there, and what is out in that gap is a population of worlds, a scattering first and then a shell, held on orbits so long and so slow that a single loop can outlast a species. The terror of the empty distance turns, when you look closely, into something inhabited. So let the vertigo settle just slightly, and turn the question toward what is actually out there. Between the Voyagers and the true edge, across all those thousands upon thousands of units the sun still governs, what exists? What could possibly be held by a grip that faint, on a leash that long? The answer is the strangest set of worlds in the solar system, worlds that never come near the planets, worlds that spend most of forever in the deep dark and only briefly, once in many thousands of years, lean back toward the light. That is what fills the gap, so we go and find them. The hold is faintest here, in the gap past the Voyagers, and yet it is strong enough to bend a whole world back after 11,000 years away. That world is called Sedna, and it is the clearest thing we have ever found in the space between the planets and the far shell of comets. Sedna is a reddish body, smaller than Pluto but not by a great deal, and it follows an orbit so stretched and so slow that it belongs to a category almost nothing else fits. At its closest approach to the sun, it comes in to about 76 times Earth's distance, already well beyond Neptune, already out past the main belt of ice. And then it turns and climbs away, out and out, until at the far end of its loop it sits around 900 times Earth's distance from the Sun, or more. One full orbit, one single trip around, takes something like 11,000 years. Let that pacing land. The last time Sedna was as close to the Sun as it is now, near the near end of its enormous loop, human beings were just beginning to plant the first crops, before writing, before cities, at the very dawn of everything we would go on to build. It has been climbing away from the Sun ever since, through the whole of recorded history and long before it, and it is only now beginning the slow fall back. For nearly all of those 11,000 years, Sedna is far out in the cold, where the Sun is a brilliant point and nothing more, and it spends only a brief slice of each orbit anywhere near the light. It is a world that visits the inner dark rarely and briefly, and spends the overwhelming majority of its existence in the deep outer dark, alone. What makes Sedna and the few bodies like it so important is a single strange fact about their orbits. They never come near the planets. The ice of the Kuiper belt was shaped and scattered by the pull of Neptune and the other giants, herded and flung by close passes with those large worlds. But Sedna's closest approach, at 76 times Earth's distance, keeps it forever clear of Neptune's reach. Nothing among the known planets could have put it on the orbit it has. It is detached, cut off from the machinery of the inner solar system, and that means something out there, or something long ago, placed it on that path and left it swinging in isolation. These detached worlds are the first members of a population that owes nothing to the planets, a population held only by the Sun's raw, distant grip and by whatever shaped them in the beginning. We know only a handful of them, Sedna itself, and a small number of others found on similarly extreme, similarly detached orbits, each one discovered by patient searching for a faint, slow-moving speck against the fixed stars. Because they spend so little of their time near enough to see, and because there is no reason to think we have caught more than a tiny fraction, the true number out there is a matter of inference rather than count. There may be thousands of Sednas, or far more. Each one that turns up extends the map a little farther out and fills in a little more of the gap the last movement left yawning. The space past the Voyagers is nothing like the blank we feared. Worlds on 11,000-year loops populate it, sparse and quiet, and we are only beginning to find them. Now ask the question these worlds force. How can the Sun possibly hold something at 900 times Earth's distance, or bend it back from even farther out, when the grip is so unimaginably weak at that range? And the answer is the heart of the whole night. It barely can. The pull out there is so faint that it would take a delicate instrument even to register it, a force thousands of times gentler than the one holding Earth in place. And yet, given enough time, barely is enough. The hold does not need to be strong. It only needs to be steady and unopposed and patient. Over 11,000 years, that whisper of a pull is enough to halt a world's outward climb, turn it around, and draw it slowly, slowly back. Sedna does not escape. It cannot. However far it climbs, the thin, unbroken grip is always there, always winning in the end, always bending the long path closed. Sedna is not entirely alone out there. A handful of other worlds have turned up on the same kind of extreme, detached path, kept forever clear of Neptune, yet still bound to the Sun. One, found in 2012, swings even farther from the planets at its closest approach than Sedna does. Another, discovered a few years later and nicknamed for the way it hides, follows a loop that carries it out to thousands of times Earth's distance before creeping back. These bodies, together with Sedna, form a small class the astronomers call the Sednoids, the loneliest of the Sun's known children, and there are only a few of them on the books so far. What makes them more than a curiosity is the way their long orbits seem to lean together. The stretched paths of these distant worlds tend to point the same direction and tilt the same way, more than random chance would easily explain, as if something were gently combing them into alignment. That faint pattern is the main reason some astronomers suspect an unseen planet far out in the dark the same Planet 9 we glimpsed at the very start, its distant gravity herding the Sednoids into their shared lean. But it is not the only possible answer, and this is where the honesty matters. The Sednoids might instead be relics of the Sun's birth, comets stolen or swapped when the Sun still sat among its sibling stars in the cluster where it formed, more than 4 billion years ago, before those stars drifted apart. They might have been lifted onto their strange orbits by a star that passed close long ago and has since moved on. We cannot yet tell these stories apart. A few dozen more of these worlds, carefully tracked, might settle it. For now, the Sednoids are a set of clues we do not know how to read, scattered across the space between the planets and the great shell beyond. Because that is what they are, in the end, a bridge. Sedna, at its farthest reaches toward the inner edge of something larger, a region where the detached worlds stop being a scattered few and become a crowd, then a swarm, then a shell wrapped clear around the Sun. The Sednoids are the near shore of it, the first lonely outposts of the true outer solar system, and past them the population only grows. Sedna itself is worth looking at closely because it is about as far from the familiar as a large body in the solar system gets. Its surface is among the reddest of any world we have found, nearly the colour of dried blood, stained by a slow chemistry working on ices of methane and nitrogen over billions of years in near total dark. Out where it spends most of its time, the temperature falls to somewhere around 240 degrees below zero on the Celsius scale, cold enough that the air you breathe would lie frozen on the ground, cold enough that most of what we think of as chemistry simply stops. Nothing happens to Sedna out there. No heat reshapes it. No neighbour disturbs it. It is likely one of the most untouched large objects attached to the Sun, a body left almost entirely alone since the beginning, creeping through the dark on its 11,000-year loop, warmed for only the briefest slice of each orbit by a Sun that never becomes more than the brightest of the stars. To hold something like that, and to hold it across 100 human lifetimes at a stretch, the grip does not need to be strong, it only needs to never let go, and it never does. When Sedna was first found, more than 20 years ago now, it did not fit any category we had. Nothing else was known on so distant and detached a path, and it was named for a goddess of the frozen sea from the far north, a fitting name for a world adrift in the coldest reaches the Sun still governs. At the time it looked like a lone oddity, a single strange body no one could quite place. Now we understand it was the first sign of a whole population waiting to be found, the near shore of the true outer solar system finally coming into view. Every world like it that has turned up since extends the map a little farther into the dark and fills in a little more of the space the Sun quietly owns. That is the lesson these detached worlds teach, the plain new thing to carry out of here. The strength of the hold stopped mattering a long way back. What matters now is only whether it is there at all. And it is there, out at 900 times Earth's distance, out at a range where you might have assumed the Sun had long since given up. A body creeps along in the deep dark for 100 human lifetimes, and the Sun, a faint point behind it, never stops reaching, never stops pulling it home. So if Sedna is held at 900 units, and held from even farther at the top of its loop, then the Sun's true reach must extend well beyond it. Sedna is not the edge but a lonely early scout in a much larger territory, the first few worlds of a population that grows denser as you go farther out until it becomes something that deserves to be called the real body of the solar system. Past even these detached wanderers lies the largest structure the Sun holds, a shell so wide and so full that everything we have looked at so far, all the planets and belts and boundaries, is a small bright knot at its centre. So we go there next, past the in-between worlds, into the great outer shell, to find where most of the solar system has been hiding all along. The hold out here is 2.5 billion times weaker than the one you live under, and it is still, faintly, a hold, and it governs the largest structure the Sun owns. This is the Oort cloud, and to understand where the solar system really ends, you have to understand that this shell, not the planets, is most of what the Sun holds. It begins somewhere around 2,000 times Earth's distance from the Sun, out past the detached worlds, and it reaches outward through tens of thousands of units to something like 100,000 times Earth's distance, roughly a light and a half year in every direction. In shape it forms very nearly a sphere, not a belt and not a disk, a great hollow shell of icy bodies wrapped completely around the sun and everything inside it, top and bottom and all sides. The number of bodies out there is beyond real counting. The estimates run into the trillions of comets and icy fragments, each one a mountain of frozen gas and dust, spread so thinly through so enormous a space that they almost never meet. If you stood on one of them, you would likely not be able to see another with your unaided eyes. They drift, each alone, across distances between neighbours that can run to tens of millions of miles, a population immense in number and yet so scattered that the shell they form is nearly empty by any ordinary measure, and every one of them is bound to the sun. Every one is falling around it on an orbit the sun still shapes, out at the ragged limit of the grip. Consider what an orbit means at that distance, because it is where the scale finally becomes something you can almost feel. A comet halfway out in the Oort cloud, at about 50,000 times Earth's distance from the sun, takes roughly 11 million years to circle the sun a single time. Not 11,000, like Sedna, 11 million, one loop. When that comet last sat at the point in its orbit it occupies today, there were no human beings anywhere on Earth, no creature that walked upright and made tools, nothing you would recognize as kin. A single year for that comet is longer than our entire species has existed, and it will complete that year in time, because the sun is still holding it, with a pull 2.5 billion times gentler than the pull that keeps you in your bed. A grip so faint it is almost a mathematical fiction, and yet real enough to close an 11 million year loop and hold it closed. This is the real body of the solar system, not the 8 planets which huddle in a bright thin disk near the centre, not the belts of ice, which are a rounding error by comparison. The great structure, the thing that takes up almost all the space the sun governs, is this dim sphere of trillions of frozen wanderers, most of them so far out that the light we see from the sun tonight will not reach them for the better part of a year. If you could pull far enough back to see the whole of the sun's domain at once, the planets would vanish entirely, a speck too small to notice, and what you would see instead is this faint, enormous ball of ice, the Oort cloud, with a bright pinprick buried at its heart. That is the shape of the solar system, honestly drawn. We live in the pinprick. And here is the hardest thing to hold about it. We have never seen it. Not one object of the outer Oort cloud has ever been directly observed sitting out there in its own place. The whole structure, all trillions of bodies, the entire shape and size of it, is an inference. We know it must exist because of the comets that fall in from it. Every so often, one of those distant icy bodies is nudged by a passing star or by the slow tide of the galaxy, and it drops inward, taking millions of years to fall, until it swings through the inner solar system as a long-period comet, blazing briefly as the sun warms it, then either plunging around and heading back out, or breaking apart in the light. From the paths of those visitors, from where they come in and how they move, we reason backward to the shell that must have launched them. But the shell itself, the source, remains unseen. It is the largest structure attached to our sun, and it is entirely a thing we have deduced rather than looked at. The shell did not form out there. That is one of the strangest parts of the story, and one of the best understood. The comets of the Oort cloud almost certainly formed close in, among the giant planets, in the warm, crowded early solar system. Then the gravity of Jupiter and Saturn, enormous and unforgiving, flung them outward, hurling them onto stretched, distant orbits, scattering them into the dark. And once they were far enough out, a gentler hand took over. The slow tide of the whole Milky Way and the pull of stars passing near over the ages lifted the far ends of those orbits and rounded them, tipping the comets out of the flat plane of the planets and spreading them into a sphere. The Oort cloud is the record of that ancient eviction, matter born beside the giant planets and thrown outward and then combed by the galaxy itself into a shell that surrounds everything. It is the solar system's own material, held at the ragged limit of the sun's reach. We meet its members one at a time when one falls in. A long-period comet is an Oort cloud body come to visit, dropped inward by some far-off nudge, taking 1 million years or more to fall, blazing for a season as the sun warms its ice, then either swinging back out on the same enormous loop or breaking apart in the light. These are the comets that arrive from any direction at all, from above the plane of the planets or below it, because they come from a sphere rather than a disk. That is the clue we set aside earlier. The short-period comets ride the flat plane because they come from the belt of ice. The long-period comets fall in from everywhere, and that alone tells you their home is a shell wrapped clear around the sun. One such visitor, spotted falling inwards some years ago, carries a frozen core roughly 75 miles across, the largest comet ever found, and it is drifting in from the outer dark on a path that takes it millions of years to complete a single loop. There is a way to see, by contrast, what the sun does not hold, and it is worth holding beside all this. Twice now we have caught an object passing through the solar system that did not belong to it, a visitor from another star, moving too fast and on too straight a path to be bound to our sun at all. The first, seen in 2017, was a strange elongated sliver that swept in, rounded the sun and left, never to return. The second, a couple of years later, was plainly a comet, but an interstellar one, born around some other star and merely passing through ours. Those objects show you the difference in the plainest terms. The Oort comets, however far out, curve back. They are held. The interstellar visitors do not curve back. They cut across and keep going, because the sun's grip, out where they entered, was never enough to catch them. The whole question of the edge is the question of where the sun's power to catch and keep finally runs out. Try to stand on one of these comets, in your mind, and feel how alone it is. The nearest neighbouring body might be tens of millions of miles away, far too distant and too dark to see, so that from the surface of an outer Oort comet the sky would hold only the fixed stars and, among them, one slightly brighter than the rest, the sun, giving no warmth and casting no shadow you could use. The light leaving the sun tonight will not reach the far edge of this shell for more than a year. Turn that around and feel the weight of it. If the sun went dark this very instant, a comet in the outer Oort cloud would keep circling a star that no longer shone for more than a year before the darkness even arrived to tell it. That is the true separation of this place, a shell so wide that its own central star is more than a year of light away at the rim, so sparse that its trillions of members almost never meet, and yet so completely bound that not one of them escapes on its own. Emptiness and ownership at the same time, stretched across the largest structure the sun holds. Consider what these far bodies actually are, because it ties the outer dark back to the ground under you. A comet is a loose pile of ice and dust, frozen water mixed with frozen gases and dark grit, a few miles across for a common one, held together weakly by its own faint gravity and the deep cold. When a comet falls inward and the sun begins to warm it, those ices turn straight to vapour and stream away, carrying dust with them, and that escaping veil becomes the glowing head and long tail we see from Earth when a great comet passes. The bodies of the Oort cloud are these same objects, trillions of them, kept so cold out there that they never warm, never shed, never glow, simply waiting. And they carry a hint of our own beginning. Some of the water that fills Earth's oceans, and some of the raw ingredients the chemistry of life needed to start here, may have been delivered long ago by comets falling in from these outer reserves, striking the young Earth and adding their ice to it. The shell at the ragged edge of the sun's reach is not only the largest structure the sun holds, it may also be a distant cousin of the water you drink, flung out to the rim 4.5 billion years ago and held there ever since, at the faint limit of the grip. So state the uncertainty plainly, because it matters more here than anywhere else in this. The inner edge of the Oort cloud is fuzzy and debated. The outer edge is worse, with estimates ranging from 100,000 times Earth's distance to twice that or more, depending on whose model you trust. The total mass is guessed at, rather than measured. We are describing the outermost, largest, most defining part of our own solar system, and we are describing it almost entirely from the behavior of the few pieces that fall out of it toward us. That should keep you honest about every confident number out here, including the ones I am about to give you for the edge itself. But grant the Oort cloud, as almost every scientist does, and one question remains, the last one. Is this shell the edge? Is the outer surface of the Oort cloud where the solar system ends? Almost, very nearly. But not quite, because the Oort cloud is defined by how far the sun can keep holding on, rather than by any wall, and its outer limit is simply the distance at which the grip finally fails. So the true edge is not the ice. The true edge is the place where even this faint, patient, 2.5 billion-fold weakened hold at last loses out to something stronger, where the sun stops being the thing in charge. So we go to that place now, the final distance, and ask what it means for a star to reach the end of its reach. The hold finally gives out somewhere between 1 and 2 light years from the sun, and the way it gives out is the last thing worth understanding. There is a distance, far past the Oort cloud's brightest ideas of itself, where the sun's pull on a loosely bound comet grows so weak that a passing star, or the slow gravitational tide of the whole Milky Way, tugs on that comet just as hard as the sun does. At that distance, the sun is no longer clearly the thing in charge. A body out there is caught between its parent star and the wider galaxy, held by both and owned by neither, and the smallest nudge can decide which way it goes. That balance point, where the sun's grip and everything else's grip come even, is the true outer edge of the solar system. It sits at roughly 100,000 to 200,000 times Earth's distance from the sun, which is to say somewhere around 1 to 2 light years out in every direction. Set that against the number we started with, and feel the whole scale of the night in one comparison. Neptune, the last planet, the place almost everyone draws the line, orbits at about 30 times Earth's distance from the sun. The true edge sits at something like 100,000 times that distance. The real boundary is more than 3,000 times farther out than the planet we call the end. Everything you were taught to think of as the solar system, every planet, every moon, every belt of ice, fits inside the first tiny fraction of a percent of what the sun actually holds. We named the small bright center and called it the whole. The nearest other star, Proxima Centauri, lies about 4.25 light years away. The outer Oort cloud, at its farthest, reaches something like a quarter of the way there. Think about what that means for 2 neighbouring stars. The sun's grip stretches out a light or toward Proxima, and Proxima's own grip stretches back toward us, and in the dark between them there is a place where the 2 reaches nearly touch. The solar system does not end at a wall with nothing beyond it. It ends where it begins to blur into the territory of the next star over. The edge is a handshake, or nearly one, between the sun's faint outer hold and the faint outer hold of a star 4 light years away. And that is exactly why calling it an edge at all starts to feel dishonest the closer you look. There is no wall out there. Nothing changes colour or texture or kind. The comets do not stop at a line. They simply grow more and more weakly bound until at some ill-defined distance the sun's claim on them fades below the claim of everything else, and a body that drifts a little too far or gets a small push from a passing star is quietly lifted away, no longer the sun's, carried off into the galaxy or handed to another star entirely. It is a fade, a thinning, a gradual loss of ownership across a stretch of space so wide that no single point in it deserves to be called the boundary more than any other. The edge moves too. This is the final uncertainty, and it is a real one. Stars pass near the sun over the ages, and each close pass tugs at the outer Oort cloud and shifts where the balance falls. The tide of the galaxy pulls steadily on the whole shell, stronger in some directions than others, so the sun's domain is not even a sphere, but a lumpy, drifting, ever-adjusting region whose outer limit depends on what has passed by lately and what is passing by now. The numbers people give, 100,000 units, 200,000, 1 light year, 2, are estimates of a boundary that breathes and shifts and has no crisp location even in principle, rather than measurements of a fixed thing. The clearest proof that this edge is a frontier rather than a wall is that other stars come and go across it. About 70,000 years ago, while our own ancestors were already walking the Earth, a small dim red star and its companion passed within roughly 8/10 of a light year of the Sun, close enough that it moved through the outer Oort cloud itself. A star crossed the outer reaches of our solar system within the span of modern humans, drifted on through, and is now more than 20 light years away and receding. As it passed, it must have tugged on the far comets, nudging some outward and loosing others to fall slowly inward, a disturbance still working its way through the shell, its inbound comets not due to arrive near the Sun for another 2 million years. The edge of the solar system is a place other stars occasionally wander into and back out of, hardly a place nothing ever crosses, brushing the Sun's loosest holdings as they go. Another such pass is already on the calendar, far in the future. A star called Gliese 710, at present about 60 light years away and coasting toward us, will in roughly 1.33 million years pass within something like 10,000 times Earth's distance from the Sun, sliding into the inner Oort cloud, far deeper than the star that passed in prehistory. It may become for a while the brightest star in the sky, and it may be the single strongest disturbance the Oort cloud suffers in the whole long history of the Sun, stirring the shell and sending a wave of comets drifting inward over the ages that follow. The planets will not feel it. The outer edge of the Sun's domain will feel it deeply, because that outer edge is exactly the region where the Sun's hold is weak enough for a passing star to matter. That is the mechanism behind the fade. Out at the true edge, the Sun no longer holds its comets alone. It shares them with the slow tide of the galaxy, which pulls steadily on the whole shell and with whatever star has most recently passed near. The boundary is set by a three-way argument among the Sun, the Milky Way, and the neighbours keep changing. The Sun's outer cloud reaches a quarter of the way toward the nearest star, and that star's own cloud, if it has one, reaches back, so that in the dark between them there is a contested zone where a given comet might belong to either or to neither for long. This amounts to a shifting, shared, ill-defined frontier rather than the tidy outer wall of a finished object, drawn and redrawn every time a star drifts past. Set all of this inside a larger motion, because the Sun's whole domain is itself only a motor drift in something greater. The Sun does not sit still at the centre of things. It orbits the heart of the Milky Way, carrying the entire solar system with it, once around every 200 and some million years, so slowly that in the whole time complex life has existed on Earth, the Sun has completed only a couple of those enormous loops. As it goes, it bobs gently up and down through the galaxy's disk, and at this moment, it is drifting through a particular wisp of warmer gas, a local cloud of interstellar material that the whole solar system is currently crossing, the way a boat crosses one patch of a wide sea. The bubble of the Sun's wind pushes through that gas, the Oort cloud is embedded in it, and just past the true edge, past the last comet the Sun can hold, that gas simply keeps going, thinning and drifting, out toward the nearest stars, whose own domains begin where ours fades. So the edge of the solar system marks the outer limit of one star's hold, rather than the edge of anything final, one small sphere of ownership in a galaxy of hundreds of billions of stars, each with its own reach, its own faint outer shell, its own drifting frontier. Cross the Sun's edge, and you have not reached the end of the dark. You have only passed from the part of it that belongs to our Sun, into the part that belongs to no one nearby, the thin common gas between the stars, where the next star's grip has not yet begun. There is a real possibility that the Sun's outermost holdings and those of its neighbours are not entirely separate. If the nearest stars carry outer shells of their own, and many of them likely do, then in the dark between two stars their faint outer clouds may reach toward each other until they nearly meet, or even overlap, in a zone where a stray comet is claimed weakly by both and firmly by neither. A body drifting in that shared borderland could, over long enough spans, be handed from one star to the other, quietly passing out of our Sun's ownership and into another's, without ever striking anything or crossing any line. If that happens, and the physics allows it, then the true edge of the solar system is not merely blurry but porous, a frontier where the Sun's most distant possessions can slowly leak away to the stars nearby, and, once in a great while, gain a stray body cast off by them. The edge is not only a fade, it may be a slow exchange, a trading of comets across the gulf between suns, carried out over millions of years in a dark so deep that no eye would ever catch a single handoff as it happened. When we found those two interstellar visitors cutting through our system, unbound and passing on, we may have been watching exactly this process from the receiving end, one star's lost comet briefly crossing another's yard before continuing on into the night. So we have followed the sun's hold all the way out, from its firm grip on the planets, through the loosening past Neptune, through the wall of the wind that everyone mistakes for the end, across the enormous gap our fastest machines have barely entered, past the lonely detached worlds, through the great unseen shell of comets, to this final region where the grip at last comes even with the rest of the galaxy and lets go. And standing here, at the honest edge of the solar system, 1 to 2 light years out, we are left with a question that has no clean answer. Because if the edge is only a fading, if there is no wall, no line, no single place where the sun's domain stops and the galaxy's begins, then in what sense does the solar system have an edge at all? We came looking for the end and found a slow surrender of ownership spread across a light year of dark. That is stranger and less satisfying than a wall would have been. It leaves the whole question we started with slightly open, hanging over the last of the distance, refusing to close cleanly. And before I tell you how I have made my peace with that, I owe you the strongest case against everything I have just spent this whole time telling you. Here is the strongest case against everything I have just told you. The gravitational edge, the one I keep calling the real end, is the blurriest of the 3 boundaries, and the only one no instrument has ever crossed or even seen. The outer Earth cloud has never been directly observed. Every number I have given for it, 100,000 astronomical units, 200,000, 1 to 2 light years, comes from watching where long-period comets fall in from and reasoning backward, never from looking out and finding it sitting there. The heliopause, by contrast, is real in a way you can point to. A count changed, a machine crossed a line, and its instruments wrote down the moment. So a careful person could argue that the only honest edge is the one the Voyagers actually passed, and that the gravitational boundary is a story we tell to make the solar system feel finished. And here is the weakness in my own argument. I have spent this whole time describing a wall where there is really only a fading, a place where the sun's hold thins so slowly that no single marker could ever sit at the end of it. Maybe the solar system does not end at all. Maybe it only stops being mostly the sun's and starts being mostly everything else's, somewhere far out in the dark where no one was ever going to stand and say, "Here, this is the line, so here is where it leaves us." Not at the last planet, not at the line the Voyagers crossed. Somewhere much farther out, in a shell of ice and dark, so wide that light itself takes more than a year to cross from the sun to its far side. The hold of the sun finally loosens and lets the rest of the galaxy back in. That is the edge. That is where the solar system actually ends. And you are nowhere near it. You are deep, deep inside. Let that be the thing you carry down into sleep. Not the size of it, which is too large to hold all at once, but the shape of it. Every boundary we found tonight sat outside you, each one farther than the last, and each one still had the sun on the near side. The planets, the belt of ice past Neptune, the place the wind slows, the place the wind stops, the long slow shell of comets that takes millions of years to turn once around, all of it, the whole enormous reach of it, is the sun still holding on, and you are held inside all of it, closer to the center than you ever let yourself feel. The machine we began with is still out there tonight. In November it became the first thing our hands ever made to sit one full day of light from home, and its small voice still crosses back to us, close to a day late, faithful and faint. It has been falling outward for almost 50 years, and it has not left. It will not leave, not truly, for another 30,000. On the scale of the real edge, the farthest we have ever reached is barely a step past the door. That used to frighten me. Somewhere in the middle of all this, it stopped. The same fact reads 2 ways, and you get to choose which one you lie down with. You can hear it as a cage, so far inside so far from any edge, sealed in by a hold you did not ask for and cannot break. Or you can hear it as the oldest kind of safety there is. The sun has never once let go of you, not for a single day of your life, not for a single day of anyone's life who ever lived. The same pull that keeps the comets turning 11 million years out in the dark is the pull under your feet right now, unbroken, patient, reaching farther than you will ever go. You do not have to do anything about it. That is the mercy of the thing. The hold does not need you awake to keep working. It bent the planets into their circles before there was anyone here to notice, and it will go on holding them long after the last person who remembers your name. You are one small thing inside a grip that spans a light year in every direction, and the grip does not tighten, and it does not tire, and it will not drop you tonight. Notice how the numbers have gone quiet now. The units, the light years, the counts and the crossings, they have done their work, and you can set them down. What is left is simpler than all of it. There is a center, and it is warm, and it is far away, and it is still holding the edge of everything from more than a light year off. You live near that center. You are closer to it than almost anything the sun owns. The dark you were turning over an hour ago is real, and it is large, and it is also entirely outside you, held at arm's length by the same quiet force that is holding you. Let the shell of comets keep turning without you. Let the two old machines keep falling outward, carrying their day-late voices into the space between the stars. Let the edge stay where it is, a light year out, in no hurry, in no danger of arriving. None of it needs your attention now. None of it ever did. You are not lost out here. You were never out here at all. You are near the middle of the only thing for light years around that could be called a home, and it has you, and it is not letting go. The bigness is still true. The smallness is still true. They were always the same thing, seen from the near side and the far side of one hold. And on this side, the side you have never once left, it feels less like falling and more like being carried. Breathe out. The sun has the edge. The sun has the comets. The sun has the two machines and the long dark and the 11 million year turnings, and closer than any of it, easiest of all to hold, the sun has you. Nothing at the edge is coming for you tonight. Nothing at the edge ever was. There is only the hold, and you inside it, and the slow certainty that it will still be here in the morning, exactly as it is now, reaching just as far. Rest now. You are deep inside. You are held. There is nowhere you need to go, and nothing out there in all those light years that can reach past the sun to take you. Close your eyes. You are held, and you are home, and the edge is a long way off and in no hurry to find you. Sleep well.